We have Gigi from Topology.
Hello, everyone. I'm Guiltygyoza. I'm with Topology, and today I will be talking about Shoshin, which is our latest experiment using Cairo VM on top of StarkNet. Shoshin is a verifiable battlefield mind. But before we talk about Shoshin, I think we want to cover a little bit about StarkNet ecosystem because it's relatively less popular in the Asia areas. So first part, I wanted to talk about StarkNet ecosystem. So what is StarkNet? What is Cairo? What are the ways that you can contribute to the open source projects, and how would you want to start learning Cairo 1.0? And then moving on to Shoshin, which is our experiment. Okay, so StarkNet ecosystem. What is StarkNet? We have Starkware people on the back. I think they will give a much better presentation later, but I'll still do a little bit of introduction. So StarkNet is a ZK rollup, and it sends state diffs, but not the whole state diffs, just the Stark proof of the state diffs to Ethereum. So essentially, you can run smart contracts on StarkNet, and everything happened there is settling on Ethereum in a trustless way using ZKP. And Cairo is your programming language to program on top of StarkNet. So if you want to run smart contracts on StarkNet, you want to learn how to program in Cairo. And Cairo is a high-level programming language. So for those of you who may have programmed a little bit in ZKP, you may know CirCom. CirCom is a relatively low-level programming language. Cairo, especially moving to 1.0, is like Rust. So it's a high-level, secure, flexible, modular programming language, relatively easy to learn. So what can you do on StarkNet? This is our experiment, timestamp October 2021. It's already 2 years ago. But what we did was we ran physics simulation on StarkNet. So then our premise was that, okay, you can do a lot of computation on the blockchain. So what would be useful to run on a blockchain? All these extra computation. Well, one thing we really wanted to do is to create virtual worlds on blockchain. And the question is, why do we want to run virtual worlds on blockchain? Because blockchains are immutable. So when you run virtual worlds on chain, its physics, its underlying laws are immutable as well. And that makes a far better world to live in than to live in worlds governed by central entities. And one of the underlying laws that govern virtual worlds is physics. So we ran physics simulation. On the left, you can see two rigid bodies constrained by springs. And this system is described in Cairo program as basically a simulation or a numerical simulation of the equation. So if you've taken classes in numerical simulation, this will be like exercise 101, simulating a linear a systems of linear equation. And as a result, we can simulate how these bodies interact. And on the right, that was MNIST tiny DNN. So that was a two-layered deep neural network that's able to take MNIST data sets, input, and return predictions, which handwritten digit it is. MNIST is kind of like a hello world of AI. And we were able to run on StarkNet using Cairo 0 MNIST inference on StarkNet. Okay, so there are many ways to contribute to open source projects. I'll just mention a few. So Kakarot on top left is a ZK EVM. Type 3 may be outdated because I think the vision of Kakarot is to go towards type 1 compatibility. And it's an interesting project because you can run EVM in Cairo, which gets proven in Stark. So you can essentially make EVM provable. And this is a different approach than Scroll and other ZK EVM projects. And there are many other projects, right? So like Mandara is a sequencer written in Rust that is blazingly fast. There are libraries in Cairo that are being created for ZKP libraries and for common data structures and algorithms. And the reason why I mention open source projects is because it's best to learn by doing. So this is the repo, keep StarkNet strange at github.com. You'll be able to find a lot of these projects, and by contributing to it, you can learn fast. So we recommend a two-step process in learning Cairo. One is to go through the Starkling tutorial, which is like a equivalence of Rustling, but in Stark. It's an interactive terminal-based tutorial. After this tutorial, you will get basically a hold of the syntax and the language features of Cairo 1, which then brings you to making something. So step 2 is build something and tweet, because the ecosystem lead at StarkNet is pretty amazing. If you build something, they will retweet, and everyone retweets, and you get to be recognized and be welcomed by the ecosystem and the culture. And that's the best way to start learning and start becoming part of the ecosystem. Okay, so after this very brief introduction, let's move on to our experiment. So quick recap. For those of you who may have not been familiar with our experiments, Isaac was the experiment we did last summer, which is a 3-body problem simulation, fully on-chain game. 3-body problem is a sci-fi story, right? That, there's a solar system with suns, and you live on a planet revolving around those 3 suns, and it's very fragile. Your planet may crash into a sun anytime, and everyone dies. So we recreate this scenario in Cairo. So there are 3 suns revolving around each other according to Newton's gravitational laws, and the planet is sort of very fickle, revolving around the suns. And the way you play this game is for all the players to coordinate and pilot the planet together, so that the planet can survive the sun, dodging the suns around the suns. This experiment wasn't going really well because there was a TPS issue back in last summer. Furthermore, we just think that this game design pattern is not really suitable for the blockchain, so we moved on from this game pattern. And that brings us to Mumu. So Mumu is a game about what we're calling a digital chemistry. Chemistry is all about synthesizing new material from other materials, right? So this game is about building a pipeline that synthesizes materials from ingredients and move these ingredients around and deliver the final product to the sink on the top right. And you want to optimize your factory pipeline to deliver as many material as possible. So this was going pretty well, in our opinion. But we thought that this is something of a bigger thing, and we wanted to find that bigger thing, sort of the design pattern that really interests us. Oh, and this is the leaderboard. So we have quite a lot of players participating in the experiment, and they're submitting their Mumu solutions, delivering different amounts at different costs and so on. So that brings us to Shoshin. Shoshin is our latest experiment about fighting. So it's a 2D fighting game running in the Cairo VM. And you will play the game by designing your agent. So you're not playing in real time with your fingers. You are playing by designing your agent, kind of like designing a mind, like a brain. And you submit that brain to StarkNet, and the brains battle against each other automatically. Okay, so the mental model basically is starting from the mind. The mind will produce an intent, what the mind wants to do, and the intent will drive the body. It's like, I think I want to move my feet, and my body responds by moving my feet. And then after the body moves around, there's physics simulation completed in the Cairo VM. And these physics simulation basically simulate the interactions of multiple bodies in the scene. That's where the fight happens. I punch you, you dodge, you jump, gravity exerts, and so on and so forth. So this is one game loop, and this game loop is repeated every single frame. Okay, so a little bit more into the game loop. As a player, you design and submit the agent's mind, and upon submission, the Cairo VM executes the following 4 steps. 1, the mind perceives from the environment. What's happening in the environment? What's my HP? What is the stamina? What my opponent is doing, and so on and so forth. Those are all perceived to the mind, and the mind computes and makes decisions on the intent. So what do you want to do next frame? That's the intent. And the intent drives the body, right? Do I want to throw a punch? Do I want to dash back? And so on. And this is run through the physics simulation, step 2. And step 3 is the physics simulation that simulates the interactions of the body. So like, okay, I throw a punch, but am I landing my punch on your body? Okay, so you are dodging back, but are you hitting the wall? If you hit the wall, you have to be stopped because the wall is not penetratable. And then step 4 is just housekeeping, like calculating how much HP everyone has left, is stamina enough, consuming, and so on and so forth. Finally, front end renders everything. So this is a fully on-chain game. The entire game loop minus graphics is on-chain, executed in this Cairo VM. But we're not doing the graphics in the Cairo VM yet. So the graphics is run on the front end, just like regular web apps that are visualizing every single frame, what happened in the fight. Okay, yet a little bit further details into the game loop. So perceptibles basically is all the public variables that you can observe about the environment. Right? So perceptibles in Shoshin right now contains your, as well as your opponent's whereabouts, velocity, acceleration, HP, stamina, and the body state, which basically is what my opponent is doing. Is my opponent jumping? Is my opponent dashing? And so on and so forth. Body counter is just a detail that basically represents which frame am I in my current animation. So these are details that we think pro player will care a lot about, hence providing this detail. Then comes to mind. So this is a AI common design pattern in the game industry using finite state machines and behavior trees. So in Shoshin, every mind is modeled with a finite state machine where every state comes with a decision tree or a behavior tree. Okay, so looking at the example on the bottom, it's quite intuitive. So I, as an agent, assuming I'm in the mental state of wait, so I'm waiting. So while I'm waiting, I may think that if my opponent is vulnerable, I will go to attack state. Otherwise, I stay in wait state. So this is a thought process going on in an agent. And this just go on every single frame. The agent thinks about which state to go and what actions to do, every single frame. And that brings us to a binary tree operator, which is our abstractions of representing the decision tree. So the app is a binary tree where every node is an operator, adding, multiplying, division, and so on and so forth. And the leaf is the operand, constants, perceptibles, and so on and so forth. This was created in Cairo 0, but obviously we need to rewrite everything in Cairo 1. And that brings us to body. Right? So the mind produced the intent. Decisions are being made in Cairo using the binary tree as a decision tree. And then the body respond. Well, in game industry standards, animations are usually represented as also, again, finite state machines. If you use Unreal Engine, you will know like anim state machines essentially is a finite state machine. So we have one finite state machine for each playable character. Like you look at Super Smash Bros. There's like a universe of playable characters, right? And these characters can do things, jump around, have special moves, and so on. Those moves are represented as usually a finite state machine per character. And there's no exception here. We also represent each character as a state machine. And that brings us to dynamics. So this is where the physics simulation happens. So we are running a two-step physics simulation. The first step is a first-order extrapolation of the physics. So essentially, if I'm moving around, I would extrapolate into the future where I might be in the next frame. And then we would need to consider overlapping. We need to handle collision. So this is common in physics engine. Collisions need to be detected and handled so that things don't overlap. They bounce around according to physics. Okay, early footages. This is before the public playtest, but we wanted to give you a sense of what Shoshin looks like. This is in the front end, the visual representation of a mind. Right? So you can see that the brain travels between states and there are transition rules. What do I do in the current state? What do I do next? And so on and so forth. This is a little programming interface for you to create custom conditions. Conditions such as, am my opponent far away from me? Or am I, is my stamina low enough or high enough? And so on and so forth. These conditions are involved in the decision making. This is an early footage of a fight between the male character and the female character. What you're looking at is the female character exploiting her special move, which is dashing into attack. So like Dashing, if you play Souls game, dashing is invincible. So when you dash or when you roll, you can evade attacks. So the male-female character is dashing into the swing and cancel that dash into an attack. And this is programmed into the smart contract so that when you cancel your dash into an attack, you skip the preparation frames of the attack. Like a startup frame. Like when you play fighting game, usually when you attack, there's like a couple frames that you're preparing to attack. And in those frames, you're vulnerable. But this female character is able to cancel a dash into attack. And when she attacks, it's immediate. She goes into the active frame of attacking. Stuff footage. This may be like quite nerdy, like fighting game player nerdy. Another footage is this, where you have the male character on the left perfectly blocking every move of the opponent on the right. And this is a frame data view. So every single frame, we provide you with the raw data for each character, every single frame, so you can debug what's happening in the mind. And this is the thought process you can also use to debug. So current focus, we've done playtesting cohort 01. We're now in a new development cycle towards the next cohort. Some photos of our playtesting. This is the QR code that you can join the waitlist. We will inform you when the next playtesting cohort is ready. Next focus is to re-architect everything in Chiron 1. So Chiron 0 is slowly being outphased. Everything needs to be re-architected, which is a great opportunity for us to rethink architecture. So on the left, you can see essentially a benchmarking. So what happens in every function call, how many Stark steps are being consumed, and so on. And we are able to recognize the bottlenecks in our game loop, and we want to optimize those bottlenecks away. Just a little statistics. So we were able to run 120 frames of fighting game simulation. That's costing 0.0004 ETH. That amounts to $0.8, assuming 1 ETH is 2K USD. So I would think that's quite acceptable. Running a complex physics simulation, fighting in a Chiron VM, costing less than $1 per fight. Imagining, like a betting happening on the side, right, for the fight. The betting may have a stake of $1,000, $10,000. So $1 to execute the fight is nothing. We also want to take the chance to re-architect and think about genericity. So when you think about Shoshin, it's not just a game anymore. It's a platform on top of which you can program minds, and minds are battling against each other. And these minds are flexible and programmable. That means Shoshin itself needs to be sort of Turing complete in a sense. So we're thinking about making Shoshin its own VM, Shoshin like application-specific VM, just for Shoshin this game. And this, of course, this VM runs in the Chiron VM, so that's a double VM. On top of this Shoshin VM, you can program mind in flexible ways as long as it compiles to the Shoshin VM instruction set. We also want to think about client-side proving. So this one is quite important. If you run computations on a blockchain, everything is public, right? So when you run Battle of the Minds and when you run it on chain, essentially everyone knows what's happening in the minds. Like the mind is transparent. But in this world, when we interact, we don't know what's happening in the mind of each other. It's opaque. And that's quite important because there may be game theory going on. I don't want you to understand what I will be doing next. So that requires us to run computations on the client side and only submit proof to the blockchain. So that basically involves functional commitment for the mind, because you can't run the mind locally and cheat by swapping mind. You need to commit to the mind. And then we would have to produce zero-knowledge proof of the fight simulation. Mind is the witness. So mind is the private input to that ZKP construct. And as a result, we can run minds battling against each other in the public, but the minds are opaque to everyone except their owner. And of course, art is really important. So we are currently going through another character art concept cycle. In every game, you would have a character with like neutral stats. Nothing really stands out, right? No really special attack moves, not really vulnerable in situations. We're trying to find that character with like the average stats, well-rounded character, maybe as a panda. And this is early work, just sketches. And that's it. That's where we stand today, Shoshin, moving to playtest cohort 02. If you scan the QR code and answer a few questions, we will let you know when the playtest is ready for you. Thank you. Happy to answer any questions. But I think in terms of which proof system to use, we haven't decided yet. So we were able to create a circum circuit that represents the Shoshin simulation. So that basically calls for verifying stock proofs in Cairo VM, and I think that may have been ready as a prototype, but as far as I know, that's verifying stock proof verifier contract in Cairo was in Cairo 0. I don't think they have started Cairo 1 work. I may be wrong. So we'll have to see if that works now. But I think overall the entire ecosystem is slowly moving from Cairo 0 to Cairo 1. So we're just taking our time, familiarizing with the new language. Yeah, that's right. So the entire execution is provable. And you have to run the exact simulation. You can't sort of run like cheat physics on your side because you have to commit to the smart contract. Yeah, that's the idea. Huh? I think it was just to re-articulate what is being proven. So the outcome of the fight is proven, and the way we prove the outcome, who won, who lost, is to prove that the entire execution of the fight is valid. But the entire execution of the fight is valid while the minds are witness, are private input. But also the minds are committed, so no one switched to a different mind in the middle of a fight. It is the mind that you submit it to. This is sort of the entire construction. Yeah, multiple fighters. So in a fighting game, you would at least fight with another, like this is 1v1. This is the basic setup. So I think...
Hey, Guiltygyoza, can you repeat the question so that the audience, people knows what the question was?
I think we're just conversing now, but I think the question is more details into what happens on client-side proving, right? So I think if I create an agent running on my laptop and you have an agent running on your laptop, and we don't want to share this with anyone else in the world, but we still want to run a fight, and that fight needs to be trustless, so everyone understands that this fight really happens correctly. Essentially, we will be trading results. So in frame 0, I run my mind, make my decision, execute simulation on my side. I send that to you, and you also run your stuff. Or maybe there's a third party that we will make our decision and send to that third party. The third party will run that simulation trustlessly. And trustlessness is completed by providing proof with every data produced, right? PCD, proof carrying data. So every data is not to be trusted unless it has a proof that can be verified. And we just keep trading these moves every single frame. And then at the end, everything is proven again. But I think we can move the proving part around. Detail here doesn't really matter. What really matters is that we are trading results around every single frame so that our mind remains opaque. We're not outsourcing the mind to anyone else.
Makes sense.
Yeah. Okay. Yeah. But I think that's also an assumption. Just want to make the case that we can, I think theoretically, we can also outsource the mind to someone else without open sourcing it. There is a way to basically break your mind into a lot of fragments and share it with a network that collectively hold the mind. As long as there's one node in that network that does not corroborate, the mind cannot be recovered. That's like one of an assumption in an MPC network. But I think there's a lot of theoretical things that might not be practical at the moment.